is Lim LEE from KGSEA Math Circle, and in this lecture we'll be discussing 3D geometry and some effective problem-solving methods. Let's start by going over the structure of today's session. First, simplifying to 2 dimensions, and 2, utilizing coordinates. These are the main methods we'll be focusing on today. A very common technique for approaching 3D geometry problems is making it 2D. This is to reduce the complexity by turning it into something more familiar. And this method works because sometimes the full 3D objects might be overwhelming, but if we focus on just 1 or 2 cross-sections, the problem can become manageable. To do this, we look at a cross-section of a 3D shape. A cross-section is essentially a slice or a cut through this shape, and it gives us a 2D view of a part of the 3D object. This makes it easier to apply our geometry techniques. So this is the first problem I have for you. I'll give you a few minutes to solve this problem, and for viewers at home, I encourage you guys to pause the video and try to solve it. I think that was enough time to get a full read on the problem. So to start off, this is how the diagram of this problem, and we can take 2 cross sections as such, with one horizontal to the base of the plane and the base of the cone, and the other vertically while passing through the height of the cone. So first we have to notice that AE plus EC is equal to 5 because the radius of the cone is 5. And second, we also have to know that since the radius of the radius of the spheres is r, the sides of triangle XEY would be 2r, and therefore EC would be 2r root 3 over 3. And finally, we have to notice that AEF is similar to ACB, and also if we look at triangle AEF, OA is the bisector of angle FAE. So since we know this by the angle bisector theorem, OE over OF is equal to 5 over 13. And after a few simple calculations, we understand that we can express AE plus EC is equal to 5 in terms of R. And a few more calculations shows us that R is equal to B. This is the second problem. I'll give you a few moments to solve this one as well. So this is the diagram of the problem. And we can first label the points where the plane intersects the top of the face of the cylinder as C and D. And the center of the cylinder would be O, such that CO and A are collinear. N would be the center of the bottom face, and M would be the midpoint of AB. Then ON is equal to 4 and MN is equal to 3 because of the 120-degree angle as given by the problem. And so OM is equal to 5. If we project C and D onto the bottom face to get X and Y respectively, then the section ABCD, whose area we need to find, is a stretching or a projection of the section ABXY on the bottom face. And so the ratio of stretching OM to MN is equal to 5/3. And since we can use the 30, 60, 90-degree triangles and circular sectors to find the area of ABXY, which is 18√3 plus 12 pi, the area of section ABCD is 20 pi plus 30√3. And so our answer is 20 plus 30 plus 3, which is equal to 53. Next up, we have utilizing coordinates. This is essential when dealing with 3D geometry because we have 3 dimensions to work with, namely the x coordinate, the y coordinate, and the z coordinate. The 3D coordinate system can be thought of as an extension of the 2D coordinate plane we're probably already familiar with. In 2 dimensions, you work with just x and y axes, but in 3D, you have the z axis, which typically represents height and depth. When working with problems involving points in 3D space, it's important to understand how to plot these points using all 3 coordinates. To talk a bit about the distance between a point and a plane. This formula might seem intimidating at first, but once we break it down, it's quite straightforward. It's an extension of the idea of finding the distance from a point to a line, but in 3D space, you're just adding an extra dimension to the mix. And for the distance between 2 points, which is another essential concept in 3D geometry, the distance formula is given with the application of the Pythagorean theorem in 3 dimensions. This is the next problem. And this is the diagram. We'll be utilizing the coordinate plane to solve this problem. First, we can scale down the whole cube by 12, and letting point P have the coordinates of x comma y comma z, and point A have the coordinates of 0 comma 0 comma 0, and with s being the side length, then we have the equations as follows. And this is because we can utilize the distance between 2 points formula that I explained in the slide before. These equations simplify into these 4, and adding the first 3 equations together, we get 3s squared minus 2s, etc. is equal to 575. Subtracting that from the 4th equation, we get 2 times x squared plus y squared plus z squared is equal to 512. And since x squared plus y squared plus z squared is equal to 256, we can find AP by scaling back the factors by 12. This is the final problem I have for you today. And this is the problem that we solved earlier using cross sections, but we can also solve this by utilizing the coordinate plane as well. So without loss of generality, let the coordinates of the center of the cone be the origin. Then let the center of the cone, center of one of the spheres be 0, comma 2r over root 3, comma r. And We should note that the distance between the points and the plane given by this Decimus graph is equal to, uh, the Decimus graph, which is equal to 2y, 12y plus 5c is equal to 60, is r, because the sphere is tangent to this plane at one point. And thus, by the points to plane theorem, we can find this equation, which finds r in terms of uh, the distance between the points to a line. And simplifying this using algebra, you can find that r is equal to 90 minus 40 root 3 over 11. So to wrap up, today we've covered some of the core problem-solving methods in 3D geometry, namely simplifying to 2D and utilizing coordinates. I hope these strategies help you feel more confident in approaching 3D geometry problems.